out. So the situation could be the following. You have a source in the middle, that's actually still the German word Quelle, where two photons are emitted, one in either direction, and each of them goes to a polarizer where we have two outputs. We call them plus and minus, the same on the other side, where the plus and minus correspond to different polarization settings. And each of those polarizers can be rotated at a certain angle. For this notation here, the left one, for instance, would be the alpha rotation, and the second one the beta rotation. And so this kind of quantum entanglement leads to correlations, meaning that if those polarizers are aligned parallel, I will find one photon coming out this arm, like the plus arm, and then the other one in the correlated arm, which is the minus. Or, and that will be random, the first photon can be in the minus arm, or the second one in the plus. Now, that by itself is not too exciting. It becomes exciting when we rotate those polarizers to different angles. So we could go to 45 degrees. And we go away from horizontal vertical, we go to 45-degree polarization, but then suddenly the same thing happens. We always get this perfectly correlated result. Plus here, minus there, or vice versa. And actually it turns out that this is, it doesn't seem very dramatic, but actually here, if we look at the correlation function between those two outputs, by looking at the probabilities for plus plus, minus minus, and so on, then it only depends essentially on the difference of the two angles. The setting, the absolute value doesn't enter. And so this means, so only the difference enters here, so the photons somehow have to get an idea of what's going on the other side. Because otherwise they couldn't react only depending on the difference of the setting. So that's a very interesting feature. So now, what became even more interesting is that John Bell discovered in 1964 that these kind of quantum correlations are fundamentally different from what we can understand in a classical world picture. So if we assume classical assumptions like that particles behave independent of each other, and also that they cannot communicate in any magic way, which we don't know about, then those correlations here, we take four such correlations for different settings, two on either side, alpha, alpha prime, beta, beta prime, and those combinations, no matter how we turn the polarizers and set choose those numbers, must always must always be bounded by the number 2. So that's just what comes out of this kind of correlation numbers. And this now means that if I have systems, again, these are the assumptions, we call it locality and realism. Systems which know beforehand what to do, or they kind of interact independently and also don't communicate with each other, then it has to keep in this bound, the correlations. However, quantum mechanics here, if we take those, we do an experiment, we take those numbers in the lab, it gives us 2.82, it's actually 2 times square root of 2. And that's a clear validation. So this means, this has deep philosophical implications. It means our classical picture of things being determined and so on, they can't be true. The concept of reality is kind of hard to maintain. Reality meaning, I know what's, so if I have something in a box, which I put inside the box, that and I close it, that I know what's inside the box. That's a kind of concept of reality. And that breaks down here. I mean, that's a very simplistic example, which would, this kind of reality here for tiny particles will be more advanced, but it's the same kind of concept. So, David Mermin wrote a nice review paper about those kind of things titled, Is the Moon There When We Don't Look, essentially. So, how do we know if the moon is not on our horizon, if it's behind the Earth? How do we know it's there? We can't see it. And why is this interesting for us now in this kind of context of space, and I'll bring this up again later. However, this can be used. So, sorry, I should start differently. First of all, it's fundamentally interesting for the quantum physics, for the philosophy, and quantum mechanics does not include a distance for this kind of correlations. However, we know quantum mechanics and relativity don't go with each other, so there must be a kind of regime where this breaks down. And this might be one route towards testing quantum validity of quantum mechanics is larger distances. So on the ground, I'll say more about this soon, but these photons can be separated maybe about 200 kilometers roughly, and that's kind of the limit. And going to space could provide the methods to separate this over thousands of kilometers, maybe millions of kilometers in the far future. But also this kind of correlation is useful for this quantum application of quantum cryptography. It should appear now. So there is the most, so from these quantum technologies, quantum cryptography, or actually it should be more accurately called quantum key distribution, is the most advanced application in the sense of towards real-world implementation. So what happens? So quantum key distribution solves the classical problem of cryptography, which is if there are two users, Alice and Bob, who want to talk to each other securely, they have to have keys which they, in whichever way they've shared beforehand. So both of them, there has to be a random sequence of bits which they both have, and then they use it for a certain algorithm to encode and then they also decode the information. Now, in the classical world, exchanging such keys is difficult. I mean, of course, there are ways to do it, but there are certain loopholes to it. If you have a courier send your CD with your key across from Alice to Bob, potentially that could have been copied, that data, or somehow manipulated, and since it's classical data, you can't tell if it's been copied. That's one loophole. The other one is it's widely used these days to have algorithms for key exchange. RSA, for instance, is one example. Those are based on computational problems which are easy to compute in one way and hard to compute in reverse. And so Alice and Bob can use that to exchange those keys. However, there again, that security relies only on the fact of computing resources that an attacker might have. Or if the keys are only secure for a certain time, you can only have, if you have such algorithmic methods, you can only be sure about that nobody can hack or undo that calculation within a certain time span, like for instance 1 year or something. And given the advances of classical computers, that's hard to predict or they can go really fast. Keys which were maybe 10 years ago thought to be really secure, these days can be hacked in maybe days or